The 0.5 N over kilograms, is that part of that, or is that from something?
That was what we've done previously. That
Okay, okay.
Yes.
What did you have the wrong one?
This right here.
Yeah.
Hewitt has an equation in the book that he writes distance is equal to 1/2 GT squared. So this is the equation that he says that you would use if you have an object that's dropped and falls in free fall. That's how far it goes in a certain amount of time. A slightly more generalized view of that is it doesn't have to always be with free fall. It can work with anything with constant acceleration. So we have displacement as 1/2 times acceleration times time squared. This is just a specific case of slightly more generalized equation. So we could have used this. Again, the condition is acceleration is constant and it starts at rest. Then we can use this. If acceleration is not constant, don't use that equation. And if it doesn't start at rest, don't use that equation. Other questions right now? I will say that on tests in the past, this is the way that people have generally done it. But some people latch onto that. That's fine. All right.
So what's the answer? How-
4 meters. Now, realistically, if I'm pushing a box across the floor, it's going to experience friction. We've talked about friction opposes desired relative motion. We haven't really talked about the formula. So let's talk about the formula. First off, there's 2 kinds of friction. So I'm using what I call the Baroque F to represent friction. The S, this is static friction. And this is kinetic friction. Try to connect my K's so it's less like a stick and curve. So static friction is the friction when something is not moving relative to what it's touching. Kinetic friction, it is moving against it. So right now, I'm pushing against this table, the table's not moving at all. Static friction is keeping it in place. I push lightly, static friction matches me. I push a little bit harder, static friction is matching me. I push harder, static friction is matching me. At some point, that static friction is, I'm going to hit a breaking point. And the static friction stops being static. Stop. Once it starts sliding, that static friction quickly becomes kinetic friction. So the static friction is always less than or equal to some maximum value. And that maximum value, well, let's think about on what it depends. What would make it harder to move this table?
The weight of the table.
Now, how would you change the weight of the table?
By putting stuff on top of it.
If I put stuff on top of it, does the weight of the table change?
No.
What changes?
The normal force.
Yes. The amount of force required to keep it from falling increases. So it's not the weight of the table itself. Putting stuff on top of it doesn't change the table itself. It just changes how much is being pressed against the floor. So the normal force depends upon, the friction does depend upon the normal force. What's something else you could do in order to make it harder to move the table?
Have an opposing force.
You could nail it down.
That's getting closer to what I was going for, and Goff, I missed what you said. Be weaker? Oh. Okay. We'll throw that into the realm of biophysics and we will then ignore it. Although, yes, a true statement. An opposing force, let's keep it simple for right now. What would nailing it to the floor do?
You wouldn't be able to move. The table wouldn't be able to move.
That's probably a bad example. Let's take a different approach. Sorry about that. So I push the book on the table, it stops. I'm hoping all of you who couldn't see the book stop, trust that it has stopped, otherwise it would have heard a thump when it hit the floor. If I did it on the carpet, easier, same, harder, would go farther.
Or it wouldn't go as far. It wouldn't go as far because there's more friction on the carpet than there is on.
So there's some special property about carpet versus table.
Oh, static.
And it's the combination of book and table versus book and carpet. Friction depends upon both objects. And this is bundled up in this thing called the coefficient of friction. So this is the coefficient of static friction. So the less than or equal to means that, again, it's matching the breaking point it's matching the force that's trying to move it until it hits that breaking point, at which point it'll start to move, and suddenly friction is now kinetic. Kinetic friction has a nice little formula, mu sub k times y, and mu sub k. Actually, somebody tell me what you think mu sub k is. The name. Say it again. Looking for a different word than mu. But you got the K part. If mu sub s is the coefficient of static friction, mu sub k is? Yes. If you were looking up the coefficients, so you type in coefficient of friction into some search engine, most likely it's going to give a table back and it'll give you two objects, and then it'll tell you the coefficient of static friction and the coefficient of kinetic friction. It'll tell you both pieces of information. If we plotted it, because everyone loves a graph, this is my friction axis, and this is my, we'll call applied force. So this is how much I'm pushing on the object to get it to move. If the object starts at rest, the friction and the applied force will match each other until you reach your breaking point. And that would be the maximum static. And once you hit that breaking point, it's suddenly going to drop off and be constant. This is what the friction versus applied force graph would look like given this model. However, there's another theory. This is working under this idea that once it starts moving, it's easier to keep moving. Friction is not going to be applied as much. It's sort of like if you imagine you've got interlocking pieces right here. It's not easy to get moving if they're already interlocked. And the more normal force means they're being pressed together even more. But once you get it moving, it's now sort of sliding across the top, and it's just easier to move. The other model of it is saying that the measurements that are done to find mu sub k and mu sub s aren't particularly good measurements. I mean, there's big error bars there. There's a big spread, and that there really is no distinction between these two. In that model, friction is less than or equal to some coefficient of friction times the normal force. This is the second model. In this model, if you looked at the friction versus the applied force, because again, who doesn't love a graph? The static would match it, it would match it, it would match it, and then suddenly it would just start moving. It seems like it would be very easy to determine which of these models is actually accurate. I've looked. I have tried to find someone who's actually done this. I found a college senior who did a paper on this, and he didn't do a lot of trials, but frankly, the error bars were so large that couldn't distinguish between the two. Almost every physics textbook that you would ever pick up is using this model over here. There are a few that do this one. There are some, like the advanced textbooks that we use here for 251, 252, use this model, but they'll spend a page on this one just saying, hey, there's this other idea out there, but we're not using it. So, back to here. My questions before we bring it back to this problem.
What is that F on the bottom?
F with a subscript of APP for applied. It's the force you're using to push it. I think there's a video where I talk about the nook and cranny model versus the attraction model. All right, so using this over here, let's just say that mu sub s is equal to 0.5 and mu sub k is equal to 0.3. Just to give you an idea of how to actually work with this. We did the force diagram. Friction's now involved. So I have this other 3 newtons to the right. I've got friction acting back. I have weight acting down and normal force acting up. So there's my force diagram for the box. Assume it takes place on some strange world where the acceleration due to gravity is 10 meters per second squared. If you want to use 9.8, go for it. We use 10. It was let's keep it as a 6 kilogram box. What is the weight of this box?
6 kilograms? Oh, ignore that.
I will.
Thank you.
The nice thing about having masks on is they don't see which mouth is moving, so I can pretend it was just the ghost in the room. All right, so I think we've established the weight is not 6 kilograms. What is 6 kilograms anyway?
The mass.
Yeah, there we go. It would have been really, really nice if everyone had said that in unison.
60 newtons.
Yes, how'd you get that?
10 times the gravitational force times the mass, the acceleration due to gravity times.
There we go. W is equal to mg, mass times acceleration due to gravity, or gm if you want to do it that way. So that's 6 kilograms times 10 meters per second squared, which is 60 newtons. what is the normal force acting on the box?
60 newtons?
There we go, yes. The box isn't coming off the ground or going into the ground, it's staying in, I guess, vertical static equilibrium. It's not moving up or down at all. Those are gonna stay balanced, so this also has to be 60 newtons. So what is the maximum static friction?
So would
60.
Not 60.
you do 60 times 0.5?
Yes. And so therefore,
30?
yep, 30 newtons. And the kinetic friction, if it's moving, what would the kinetic friction equal? All right, so what is the acceleration of the box? Here's the hint, you don't need a calculator for it. Ethan, what was that?
3 newtons per kilogram.
Nope. So I got a box that's sitting there on this floor with friction. I'm pushing on it with 3 newtons of force. How much force do I need to apply to get this thing to move?
60 newtons.
Not 60. Yes. This is what I need to overcome. This is the breaking point. I'm applying 3 newtons and I need 30 in order to get it to move at all. So it's not moving at all. Therefore, what's the acceleration?
0?
And then don't forget units.
Wait.
Acceleration.
Oh.
There we go. All right, now here's the next tricky question, which is really a whole lot simpler than some of you will think. How much friction force is being applied to the box? Yes, there we go. Because the static's gonna match me. It's gonna match the applied force until you hit the breaking point, and I know we're close to the breaking point. If I applied 30 newtons of force, assuming all these numbers are significant, if I applied 30 newtons of force, I'd be right there at the breaking point. If a gnat came along and landed on the box on the side that I'm pushing, so a gnat comes along, hits the box, that box would then start moving, and the friction would drop down to 18 newtons.
So it has to be greater than.
Yeah. Now, in reality, it's a fuzzy boundary there, but we pretend. But F equals ma, that's Newton's second law, that's chapter 4. Questions? That is simple if you have a question, or, okay. No, but, just trying to make sure I wasn't ignoring you. All right, so, what we have here is I have a cart, a relatively flat track, and that flat track, and it should, put that on. And so I'm gonna apply a force to it, and we're gonna see what kind of acceleration we get. Hardly much there, probably more than that. I'm gonna trust that the front on here is correct, that I'm putting 100 gram mass on the end of the string. Despite the fact that we just talked about friction, we will assume that the friction is so small that we can ignore it. I have gone through experiments where I've actually tried to calculate the friction in these situations, and it is indeed so incredibly small, we can ignore it. Matter of fact, I've seen enough of these experiments where you end up with negative friction, which means the friction is not harming movement but helping it. Yet one more Nobel Prize heading towards one of my students. All right. So I've got a cart on wheels, I've got pulley, hanging mass. All right, so I care about the cart and the hanging mass. So cart and hanging mass. There's a rope there, which, what the heck? Let's do the whole thing. Force diagram. All right, what force is acting on what and in which direction?
Weight
Acting
on the mass down.
on this?
Yes.
This of each. Okay. See? Okay. What else?
The normal thing up.
On
Cart and then box. Whatever the H1 stands for.
hanging mass.
Yeah.
All right, so normal force acting up on the cart and the hanging mass.
Yes.
All right, is she right?
No.
Not only hanging mass, just on
Just on
seat.
the cart.
Right. Hanging mass isn't touching anything other than the rope, and we're gonna handle that under tension. So it is hanging up on the cart, absolutely, twice MC, and then down on the table. And then for the hanging cart, there's no normal force. So we've got weight and normal force done. There's no other. We're ignoring friction. And tension.
Tension from the cart